Greetings and welcome to what I think is probably the most ambitious technical video that I have attempted. And it's going to be on a topic that I've had several requests to do, and that is phase inverters. Now, phase inverters are, I think, the most complex and least understood part of the amplifier. They're also probably the hardest to explain. But I think I boiled it down to fairly simple concepts and language here that should make it very clear to you. And all I ask is that you give me a chance to explain it, and I think by the end of this video series, it may take 2 videos, I think you will have to admit you know a whole lot more about phase inverters than you did before. First, let's talk about why phase inverters are necessary. In single-ended amps, there is no need for phase inversion. Single-ended amps, as you all well know, have one output tube. They are generally Class A amps. They operate at a fairly high idle current. They produce a lot of heat. They're not terribly efficient, but they have great tone, and we associate them with some of the classic amps of all time like the Fender Champ. But just like a one-cylinder engine is nowhere near as powerful as a two-cylinder engine, once you have 2 output tubes, the output power capacity is much, much greater. Also, if you have 2 output tubes, there are several other advantages. They tend to cancel out hum. They tend to accentuate even order harmonics. And also, they then operate in an A-B mode, which in simple language means that the idle current is much lower, so they produce less heat, and they are more efficient than a single-ended amp. But when you decide to use 2 output tubes, you come up with a little problem, and that is that you have to have a center-tapped output transformer. One end of that transformer connects to the plate of one of the output tubes. The other end of the transformer connects with the plate of the second output tube. The transformer is center-tapped, and the B+, or the high voltage, the high positive voltage produced by the power supply, goes here to the center tap and flows through this winding to this plate and through this winding to this plate. Now, as we learned in the How Do Amplifiers Work video series that I recently posted, not only does the B+ flow this direction to the plate, but the amplified output signal from the guitar or instrument flows the other way, back through the output transformer. Remember, we found that direct current, which is the B+, and alternating current, which is the guitar signal, can flow through the same wire at the same time without any mixing. So we'll use the output transformer to feed the high positive voltage to the plates. That makes them into vacuums, as you remember, for the electrons that are coming from the cathode. And also then we're going to send the amplified signal to the output transformer, and it is going to change it from a very, very high voltage, low current signal into a very rather low voltage, high current signal that will operate the voice coil of our speaker and make our amplifier work. Now, here's where the problem arises. Because it's a center-tapped output transformer, when we feed the signal in from this plate here and from this plate here, if you notice, we're feeding in at opposite ends of the transformer. Now, think of the center tap as a mirror. And it's like it's reflecting, and where this right here is a mirror image of this down here. Now, what that boils down to is this. If we have a signal that looks like this, and it's going to rise and fall, it's sort of like an S that's tipped over in a counterclockwise direction. If we feed this signal in right here to this tube, and it comes out the plate, and we feed another identical signal to this grid down here, and it comes out of this plate, the signals then are in phase. Let's imagine that this portion of the output transformer is a horse with his head pointed in the plate connection direction. Down here, another horse with his head at the point where the plate connects, and the horses are tied together. Also, these horses are specially trained. When they receive a positive signal, they walk forward. When they receive a negative signal, they walk backwards. So let's send them an in-phase signal. Both of them then at the same time will receive a walk forward signal, a positive signal. This one tries to walk forward, this one tries to walk forward, they're tied together, they go nowhere, a lot of wasted energy. Next, they receive both negative signals. They both try to go backwards. They back into each other, they go nowhere. Again, wasted energy, nothing. The net output of them pulling in different directions or pushing in the same direction, the net output is 0. Now let's send this horse the same signal. It's rising, it's positive. He wants to go forward. But let's invert the signal to the lower horse. So when this one receives a positive signal and wants to go forward, this one receives a negative signal and wants to go backwards. Okay, their joint force, their individual force is combined, and we have a much greater force moving in one direction. Then when on the next cycle, this horse up here will receive the negative signal and want to go backwards. This horse down here will receive the positive signal and want to go forward. They both go in the same direction and their forces are combined. So when the signals are out of phase, the output is maximized because both arrows are going in the same direction. So now hopefully we see why we have to have a phase inverter if we're going to have two output tubes and if they're connected to the opposite ends of a center tapped output transformer, which is the way they always are connected. For such a complex subject, the rules are actually quite simple, and there's only two of them. Okay, number one rule, if you drive the grid, in other words, if you put the guitar signal into the grid of a tube, the cathode will follow and the phase will remain the same. We put a rising positive signal in on the grid, the signal in the cathode will be exactly the same. The cathode follows. But if we drive the grid, the plate will invert the signal so that the signal that we send into the grid will create a mirror image or out of phase or inverted signal from the plate. So let's say to ourselves, our mantra for today is, if we drive the grid, the cathode follows and the plate inverts. And now the second rule is, if you drive the cathode, and this may seem strange, but you can actually send the signal, the amplified signal, into the cathode of a tube. You don't always just have to drive the grid. But if you do send the signal into the cathode and drive it, the signal on the plate will be in phase. So if you drive the cathode, the plate does not invert. Okay, that's our second mantra. If you drive the cathode, the plate does not invert. Okay, hopefully that introductory information made sense. If not, you might go back and look at it one more time. But if you feel like you're ready, let's continue and look at three specific types of phase inverters, which cover almost every type of phase inverter you'll ever find in an amplifier. The first one is the simplest. It involves a single triode phase inverter. It's called the split load, or an older term, a Cathodyne phase inverter. And this should be very simple to understand if you remember that when we drive the grid, the cathode follows, the plate inverts. So let's send our guitar signal in here to the grid of the phase inverter tube. In this case, it could be 1/2 of a 12AX7. Well, we said that the cathode follows. So look, here is the input signal. Here it goes from the cathode of the tube. It looks exactly like the input signal. They are the same. It's going to go over here to the grid of this output tube and going to be sent to the end of the output transformer from this plate. But remember, when we drive the grid, the plate inverts, so the signal that comes in here to the grid of this phase inverter, or 12AX7 half, comes off this plate, and it is the opposite. It is inverted. It is out of phase with the initial signal. So we have exactly what we need here. We have one signal that's unchanged and one signal that is inverted or out of phase. We send them to the output tubes, and they come out here, and the horses pull in the same direction. Now, this method of phase inversion is used in the Fender Princeton, the Fender Harvard, the Gibson GA40, and a whole bunch of other amps. It's a fairly inexpensive, basic way to have phase inversion. If you notice here, this is the plate resistor, and this is the cathode resistor. And because we want these signals to be of equal volume or equal amplitude, because I want this tube to drive the output transformer exactly at the same power as this tube, I want a balanced signal, then these resistors should be the same. We're going to see in some other types of phase inverters, we're going to change resistance here and there to sort of vary that and balance the signal. Now, the advantage of this style of phase inverter is it's cheap, it's simple, very basic, but you don't get something for nothing, okay? You do lose out on the fact that one of your stages here, which your phase inverter stage, has no gain. Remember, the purpose of an amplifier is to amplify. Well, this type of phase inverter does not increase the volume of the signal. Well, let's face it, if you bring in a signal here and split half of it this way and half of it this way, there's no way that it's going to get louder. If anything, it gets a little lower in volume. So the drawback of the split load or Cathodyne phase inverter is that there is no increase in volume in the phase inversion stage. Now, just so you know, I'm not making this stuff up. Let's take a look at a Fender Princeton Reverb amp. Now, here are the two output tubes. They're 6V6s. And look over here. This is the phase inverter. It is a split load or Cathodyne phase inverter, as we just discussed. Look up here. The plate drives the grid of the upper 6V6, and the cathode drives the grid of the lower 6V6. It's exactly like the diagram. And also, as I promised you, the plate resistor is 56K, and the cathode resistor is 56K. Also notice the coupling capacitors that are always necessary to keep the direct current on the plate away from the grid of the next tube. So we have coupling capacitors here and here, and I've included them on my diagrams. Okay, now let's look at the second type of phase inverter, and that is the Paraphase phase inverter. This is a sort of an old-fashioned method. It was used in the Fender 5C3 Deluxe. It's used in some of the Newcomb amplifiers that you may see in some of my videos. Okay, and we're going to have two triodes. So it's more complex than the Cathodyne or split load because it's, well, actually twice as complex. There's two triodes involved. You do get gain in that this stage will not only phase invert but also increase the volume of the signal. Okay, so you do get something for the added complexity. Let's look at it. It's very straightforward. We bring the signal into the grid of the first of the phase inverter triodes, and remember, it's a rising signal here. rising to the positive direction. And the output, because remember, when we drive the grid, the plate inverts, is reversed, it's out of phase, it's inverted. We feed that in through the coupling capacitor to the grid of this output tube. Now, we take the inverted signal, send it down here, and let's feed it into the grid of the second phase inverter triode. And I think you know what's going to happen here. When we drive the grid with this inverted signal, the plate inverts the inverted signal, and we end up with a signal that's back to exactly the way it was in the first place, which is in phase with the input signal. So now we have the out of phase signal going to this end of the output transformer. We have the in phase portion of the signal going to this end of the output transformer. The horse pulls, they both pull in the same direction, and we get a really big, strong output signal. Now let's look at one final little detail here. Remember I showed you the resistors, the 56K resistors on the split load or Cathodyne phase inverter. Well, let's look at what we have to do here. Now, I've sent my signal through one triode. I didn't split it, so I do get gain here. Then I send, remember, this inverted signal down here to a second triode. Wouldn't it make sense that this signal would be a lot louder, a lot stronger, because it's been through two tubes, whereas this one's only been through one tube? Let's put a resistor here and leak some of the signal off from the grid so that we sort of turn the volume down on this signal and balance it so that the output from the second tube is of the same amplitude, although opposite phase, from the signal that comes out of the first tube. So as you can see, you have to do something. When you go through two tubes, you have to suppress the volume of that signal, or else this one would be driving the phase and the output transformer a great deal. This one would not. The horses would be pulling in the same direction, but at very different amounts of force or strength, and it just would not be a coordinated effort. If both of the signals are balanced, you'll get a lot better result. Now let's look at a real schematic and see how this actually functions in real life. Okay, this is going to be an early Fender Deluxe schematic for the 5C3. As I told you, this is sort of an old-fashioned method. Okay, just like in the previous diagram, the plate up here, this is going to be two triodes. They're in a 6SC7, a very kind of older style of pentode tube. And like in our diagram, the plate of one of the triodes is going to drive the grid of this 6V6. Now let's see what happens. We're going to bring our signal out here, and instead of sending it all to the grid, we bring it down here and feed it into the grid of the other triode. So remember, this signal up here was inverted because when we drive the grid, the plate inverts. And then we send the inverted signal down here to this grid, and when we drive the grid with an inverted signal, the plate inverts it back and sends it into this grid of the other 6V6. Which leads us to the third and final type of phase inverter, and it's the most famous and most widely used. It's called the long-tailed pair phase inverter, used in the Fender Bassman, the Concert, the Bandmaster, a bunch of Marshall amps, all sorts of amplifiers use this method for phase inversion. As you can see, it utilizes two triodes just like the Paraphase inverter that we just discussed did, except they're arranged in a very different manner. Here's our input signal driving the grid of the first triode. By now you should see immediately what's going to happen. When we drive the grid, the plate inverts. Look up here, here comes our signal, and you can see it's inverted, and we send it in to the grid of the output tube. Okay, so this is very much like, at this point, like the Paraphase. Drive the grid, plate inverts, send that signal through the coupling capacitor over here to the output tube. Now, instead of sending some of our plate inverted signal down here to the grid of the lower tube like we did in the Paraphase, let's connect the cathodes of the two tubes. You see, that's the fundamental difference between this and the Paraphase method. We're not going from plate down here to grid like we did in Paraphase. We are going to connect the two cathodes. Remember that the cathode follows the grid. So if we have an in-phase signal coming into this grid, the cathode's in phase, looks like this, and it will come down here and this cathode will be in phase. Now remember rule 2, if you drive the cathode, the grid does not invert. So I'm going to send my cathode followed in phase signal down here to this cathode, and when I do, it jumps here and stays in phase. So my upper 6L6 or whatever type of output tube we have here has a inverted phase signal going to the grid. The lower 6V6 or 6L6 has an in-phase signal because we took it from the cathode of the top tube, sent it to the cathode of the bottom tube, and according to rule 2, if you drive the cathode, the grid does not invert. So here we go, and we've got just what we need. Signals that are in opposite phase from each other. We feed them in to our output tubes. They come over here to the output transformer where they now cause the horses, if you will, to pull in the same direction and give us a huge output signal. Now, since I talked about resistors on the other two, this is probably the most interesting of all the resistor analysis that you might see on one of these, as if resistor analysis could be interesting. But I always wondered when I looked at a long tail pair, why is this resistor generally 100K and this resistor 82K? It drove me crazy because it looks like, look, here comes my B plus in here. It's going to be feeding my tube plates. Okay, and it's like I'm being mean to this tube by putting a larger resistor in line. It's like you have two kids here and you're giving this one up here more cookies than this one, because the lower the resistance, 82K, more of the B plus will go to this plate. Higher resistance, we're cheating this plate, or so it seems. Well, remember what we had to do in the Paraphase phase inverter, because remember here the signal is going through one tube, and in this one the signal is going through two tubes. So we have to cut back on the B plus, the plate current and plate voltage that we apply to this tube, because we have to lower its output a little bit, because remember this signal is the product of two tubes. This signal is the product of one tube. So we put a larger resistor here to lower the plate voltage here to bring this signal down to where it's equal to its inverted twin. Now, as we've done with the other types of phase inverter, let's look at a real one here. This is the Fender Bassman, the classic AA864 Fender Bassman. Look here, see where the cathodes are connected together, right there, as I showed you in the diagram. We're feeding the signal in here to the grid, and this is a 12AT7. Rather unusual phase inverter, but very made famous by Fender. We bring the signal in here to the grid of this half of the 12AT7. The plate sends the signal right over here to the grid of the 6L6. Exactly like the diagram, very straightforward. But the difference is that we tie the cathodes together, And remember that the cathode follows, and there is no inversion here. So this signal up here is inverted. This signal down here is not inverted. And sure enough, there's the 82K resistor, which brings the B plus up here and gives more plate voltage to the upper triode than the lower triode, since it goes through 100K of resistance. So you see here, this imbalance is what compensates for the fact that the signal has gone through only one tube up here and gone through two tubes down here. Well, that about does it for this presentation, and it appears that it's going to all be in one video. Hopefully the majority, if not all of it, made good sense to you. If you're still puzzled about parts of it, the beauty of having this available to you on YouTube is you can go back and review those parts, and hopefully they will become clear for you. I know that my analogies and leaving off certain little details will probably upset all the electrical engineers in the crowd. But for those of you who are like me, that want just to have a basic understanding of how these amps work, you're my target audience, and that's the way I directed this presentation. And I hope that it's taken the same way. So I appreciate your time and interest. I hope this made sense. I hope you know more now than you did before, and I hope to see you again in the near future. Thanks so much.